first thing we covered in this unit. Very first day we talked about the structure of the atom, the history of the atom, okay, and kind of models and the atomic theory. Okay, that was all the first day. Right? Now, what do you need to know from that lesson? Key people. Okay, if they did something important, you should probably know them. Like Dalton, for example, I would say probably one of the important people. He did, after all, come up with the atomic theory. Okay, which also something pretty important. Okay, I would say you need to know the 4 points of the atomic theory. What are they? You remember? Okay. Whichever one. You don't have to name them all. Give me one.
In chemical reactions, atoms are rearranged, separated, and
Joined. That was the one you missed. Yeah, absolutely. Okay, they're not turned into other elements. Okay, that's actually point number 4. Okay, we'll take it. What else?
All materials made out of indivisible tiny particles called atoms.
Awesome. Point number 1. Okay. What else? Atoms can combine in simple whole number ratios. That's usually the tricky one. Good job.
Atoms of the same element are identical.
Atoms of the same element are identical. Okay? Those 4 points. Now, I'm probably not going to ask you to write them down verbatim like I did on that one quiz. Okay? But I would know them for maybe a multiple choice question, like, you know, which of the following is not part of Dalton's atomic theory, you know, or something like that. I'd have 4 points there. 3 of them would be, 1 of them wouldn't. Okay, stuff like that. Just be, you know them to recognize them. Who proved the existence of the nucleus? Rutherford, with his what kind of experiment? Gold foil experiment. Okay, another one, kind of important, probably a multiple choice question, something like that. Okay, you know, Chadwick, okay, like neutrons, and Thomson electrons, like somebody who did something big, and it would just be multiple choice. So the answer would be in front of you, you just have to recognize it. Okay, know the models. Okay, know like plum pudding or Rutherford, you know, or whatever, and especially know our currently accepted model, which is whose? The de Broglie guy, yeah. Okay, de Broglie's electron cloud model. That's our currently accepted model of the atom. Now, why do you need to know that? Because I will ask you this. I will ask you to draw me a picture of an atom of, and I'll pick an element. Okay, what I'm going to want is the right number of protons, the right number of neutrons, the right number of electrons. I'm going to want them in the right places in the right model. 5 marks. Okay, so if, in theory, I asked you, draw me a picture of an atom of sodium. Okay, how many protons would I draw? 11. The atomic number is the number of protons. The number of protons, which are positive, has to equal the number of electrons, which are negative, because any element is electrically neutral. The number of positives and negatives are the same. So when I draw this atom, I'm going to have 11 electrons and 11 protons. How many neutrons am I going to draw? 12. Okay, how do we figure that out? That's where we take the atomic mass and we subtract the atomic number. So effectively 23 minus 11 is 12. So what I would want to see as an answer to that question would be should have picked a smaller atom. Okay, so I've got 23 particles there. Okay, I'm going to put 11 protons in there. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now I've got 11 protons and I've got 12 neutrons. That's my nucleus. Okay, and then I'm going to draw my cloud and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and then maybe a legend. Might not be a bad idea, right? Like proton, okay. Get the idea. 5 marks, right there, that's all you have to do. Okay, show me, you know how to get the number of protons, the number of electrons, the number of neutrons. Okay, you know what our currently accepted model is, you know where everything goes. Okay, questions there? All right, so first day, that's what we did. Structure, history of the atom. So know all the parts, okay, things like that. That would be important, okay? Our currently accepted model, and obviously the 4 points of the atomic theory. Okay, probably before we go any further, we should talk format. What is your exam going to look like? Okay, it will have a multiple choice section. It will have a numerical response section, and it will have a written response section. Okay, so multiple choice, when you know how that works, you'll have a bubble sheet. Okay, you shade in A, B, C, or D. Okay, now on that note, you've all done a scan form before. Okay. Read through the question, and the first time you write your answer in pencil, make sure it's in pencil, okay, just put like a little X in the box. Light little X, in case you change your mind later. Some people do, okay? Because then that's easy to erase. Here's what I see a lot, actually. They read the question through, and they are certain that the answer is D. So certain that they leave no little part of that circle unshaded. It's all done, okay? And it's dark. And then they're, oh shoot, I read that wrong. Oh no. No, the answer is actually A, and I'm just as certain of that as I was of the D before, so I'm gonna shade it real dark, okay? And then they do this. And then they go, oh no, 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 it's actually not. It's actually. And then they do this. I know artificial intelligence is getting better, but, okay, the app that I use to scan your answer forms isn't artificial intelligence. Okay, it is a simple computer app. Do you know what it tells me when it scans that? That it's wrong. Because you know how many right answers there are? 1, not 3, okay? But the app sees you shaded in 3 things and it goes, you're wrong. And it's right when it says that you're wrong, okay? Even if that is the right answer, it doesn't know what that means, okay? In fact, it usually screws it up. I am not manually checking a machine-scored test. The whole purpose of making a machine-scored is to save me time. So don't do that, okay? Just a little X. Okay, that you can easily erase if you want to change your answer. Everybody good with that? I say that, I'm still going to see that at least once. Okay, don't do that. Okay, pencil. If you don't have a pencil, ask me for one. I will get you a pencil on exam day. Okay. Numerical response. You've done numerical response as well. Okay, if you did like a PAT, you've definitely done numerical response question. So kind of 2 ways that a numerical response question can go. One of the ways, first question you're going to get, is 7 reactions that have to be balanced. Okay, so if I get this reaction here and I balance it, okay, so all right, biggest number is 2. All right, so I need a 2 there, and then a 2 there, and this will be a 1 and a 1. Okay, so now for the numerical response, you'll have your block, okay, where you would go 2, 1, 2, 1, and then underneath that will be the bubbles, right? So this would be like a decimal point, this will be like a 0, a 1, 2, 3, it usually goes up to 9, okay? And then you would fill those in. So this one's a 2, so you'd fill that one in. That one's a 1, so you'd fill in the 1, and then you'd fill in the 2 for this one, and the 1 for that one, and that's how that would work. Okay, that's one type of numerical response question. The other type of numerical response question might ask you, here's a situation in which some of the concepts from this unit apply. So it tells you a little story. Okay, and then it gives you a list of concepts. And your job is to pick the concepts that are part of that story. Okay, so if I gave you, let's say, a story about, I don't know, maybe it's about like how trees transport water from their roots to their leaves, okay? And some of the options might be the polar nature of water, adhesion, cohesion, Dalton's atomic theory, solubility. Okay, you wouldn't pick solubility, that's not part of it. Dalton's atomic theory has nothing to do with it, but plants use the polar nature of water, adhesion and cohesion, to help move water up the stem. Okay, so that would be another way in where you just fill in the numbers. Okay, it was concept 1, 4, and 8. Okay, that's the other way. But they all work fundamentally like this. You'll have a row, there'll be a certain number of numbers you'll have to write in and fill. Everybody with me there? Okay, and then you'll have written response questions. Those will be like writing out, predicting the products of a chemical reaction, writing it out, your mole equation calculations, okay, things like that. Okay, where you actually have to do the whole thing. Okay, any questions on the format? All right, let's go back to the beginning here. Okay. Okay, so number of protons, so this all goes. Okay, next concept, naming / writing the formulas for chemical compounds, molecular compounds and ionic compounds. Okay, quick review. Ionic compounds are made of a metal and a nonmetal. Okay, molecular compounds are 2 nonmetals. Okay, you'll need to know that. You'll need to know kind of their differences, like in a molecular compound, the electrons are shared, versus in an ionic compound, they're traded. Okay, things like that could be multiple choice questions for sure. As would naming and writing formulas. Okay, so I could have a multiple choice question says the proper formula for sodium chloride is A, B, C, or D. Okay, or the correct name for BeCl2 is A, B, C, or D. Okay, definitely there'll be that in the multiple choice. Okay, so it's pretty simple stuff. All right, but let's quickly review, okay, our naming and formulas stuff. Okay, here just because it's been a while. Okay, when do I use Roman numerals? If it's ionic and the metal has more than one charge, yeah. Okay, usually two on our periodic table. Okay, so that's when I would use a Roman numeral. Do I use it in the formula or the name? Only in the name. Okay, what kind of compounds would I reduce the little numbers in? Molecular or ionic? Ionic, right. Okay, because in molecular you're told prefixes. The prefixes are gospel. If it says di, it's 2. If it says penta, it's 5. Okay, you don't try and reduce molecular ever, but you always reduce ionic when possible. Okay, all right. So then, don't forget our special elements. It is okay if you have those marked on your periodic table. Okay, you are going to get to use your periodic table on the exam on Monday, provided you have not written too many notes to self on it. Okay? Here's what I would accept. The prefixes, the Roman numerals, the special elements, maybe you could put charges in there. I'd probably be okay with that too for some of those nonmetals that didn't have the charges in. Okay? Anything more than that, that's going to be too much. Okay? But I would certainly allow those things on there. If I see more than that, I'll give you a fresh periodic table. Okay. So let's just do a quick review here of some naming and stuff. Let's do. Okay. Give me the names for those 5. All right. So question number 1. Ionic or molecular? Ionic. Lithium is a metal. Okay, so the rules for writing the names for an ionic compound are I write the name of the metal, and then I write the name of the nonmetal, but I make it end in I. Okay, so this would be lithium nitride. I don't need any Roman numerals because lithium only has one possible charge. Okay, it's ionic, so there's no prefixes. Simple as that. Ringing a bell? Okay. Number 2, ionic or molecular?
Molecular.
It's molecular. Those are both non-metals. So in molecular compounds, okay, I also need to use prefixes. Is this correct, or should I have reduced this? Right, I don't reduce this because it's molecular. I never reduce molecular. Okay, so this is going to be diphosphorus tetrachloride. Okay, questions on that one? All right, for number 3, ionic or molecular?
Ion.
This is ionic. Iron is a metal. Okay, so I follow my ionic rules. I write the name of the metal. I write the name of the non-metal, ending in "ide." Anything else I need to do for that one? This one needs Roman numerals because iron can be a 2 or a 3. So I've got to figure out, is it the 2 or the 3? To do that, I look to the non-metal. Iodine is always a -1. There are 2 of them, so that gives me 2 negative charges. That means I need 2 positives from my metal. There's only 1 iron atom here, so it must have a charge of +2. So this is iron, Roman numeral 2, iodide. Okay. All right, number 4, ionic or molecular? Ionic. This one, though, has what in it? A polyatomic ion. Okay, that doesn't really change the rules very much. I still write the name of the metal, copper, the name of the non-metal, this time it would be the ion, sulfate. Okay, anything else I need to do with that? I need a Roman numeral. Copper can be a 1 or a 2. Okay, sulfate is always a -2. How many sulfates are there? 1. Okay, so that means I've got to get 2 positives from the copper. So it's copper, 2 sulfates. Okay. All right, and then number 5, ionic or molecular? It's ionic. Lead's a metal. Okay, so write the name of the metal, lead. Write the name of the non-metal, nitrate. Okay, anything else? Roman numeral. Lead's got more than 1 possible charge, 2 or 4. Okay, nitrate is always a -1. How many nitrates are there? 2. Okay, so I've got 2 negative charges. There's only 1 lead to get that 2 from, so this is lead 2. Nitrates. Okay, now jumping ahead here. Is this compound here soluble? Okay, lead 2 nitrate. Yes, it is. Okay, if you look on your solubility chart, nitrate is soluble with most, and then there's some really weird things underneath that for the things it's not soluble with. Lead would be part of most. Okay, is that something I'll ask you to do? 100%. Probably in the same way I asked you to do it in your reactions lab, where I said, here's a reaction, which, if any, of the products are soluble. Okay, and you guys had to look in there and go, okay, so sodium chloride is soluble, but potassium iodide is they're both soluble, so both are soluble. Right? It would be a multiple choice question, and you'd say like sodium chloride, potassium iodide, both, neither. Okay, you'd answer like that. Okay, let's go the other way. Here are the names. Give me the formulas, please. All right, first one, ionic or molecular? Molecular. They're both non-metals, and there are prefixes, which only happens in molecular. All right, so the first thing is sulfur. How many?
3.
Mm-hmm. Okay, and how many oxygen?
2.
All right, simple as that, S3O2. Okay, number 7, ionic or molecular? Okay, so when we do ionic ones, we write the symbol for the metal, and we write its charge, sodium's a +1, and we write the formula for the non-metal, and its charge, oxygen's a -2. Okay, then we drop and swap. Okay, do we write ones? No, it's incorrect to write ones. Na2O, done. Okay. All right, number 8, ionic or molecular?
Ionic.
Ionic. We only use Roman numerals in ionic, and cobalt is a metal. All right, so cobalt. Which cobalt? 2 or 3? 3. The Roman numeral tells me it's 3. Okay, and it is with sulfide. That's S. Sulfur is always a -2. What do I do now? Drop and swap. CO2, S3. Done. Can't reduce that, so I leave it the way it is. All right, number 9, ionic or molecular?
Molecular.
All right, it's molecular. Okay, how many phosphorus?
5.
All right, how many fluorines?
10.
Should I reduce that? I better not. It's
Molecular.
molecular. Okay, now, if I put that one on a test, obviously P5F10 would be one of the possible answers. But so would PF5. Okay, and some people would pick it because they would over-apply that reduction rule, right? They go, oh, I'm supposed to reduce, I can reduce both of those. You can, but not in this one. You don't reduce, okay, molecular compounds. Okay. All right, and then for number 10, iron 3 carbonate, ionic or molecular?
Ionic.
Ionic. Okay, so I write the formula for iron. The Roman numeral says it's a 3+ charge. Okay, and then I write the symbol for carbonate. CO3, it's a -2 charge. Drop and swap. 2 goes here, 3 goes there. What do I need?
Brackets.
Right, otherwise it's CO33, not CO3, 3. Okay? Ringing a bell? Okay. Something to practice, have a look at, okay, over the next few days. All right, next thing we did was properties of compounds. This is lesson 4 in your notes package. We also did a lab using everything we learned in lesson 4 about physical properties. And in that lab, we used just the physical properties of the unknown compounds to assign their identity. So in this lesson, I taught you things like ionic compounds are all crystalline solids at room temperature. Okay? They are generally soluble in water. Okay? When they dissolve, what do their solutions do? They conduct electricity, right? Because they split into the positive and negative ions that they're made out of. Okay? Whereas a molecular compound, even if it did dissolve, wouldn't conduct electricity. Okay? So things like that. Okay? We're in that lesson. What do you need to do with that lesson? You need to read it over. It's kind of a memorize and regurgitate kind of a lesson. Okay? Now, we did use that, obviously, in our lab. So it's feasible that I might ask you a multiple choice question like this. You have a pink crystalline solid that dissolves easily in water, whose solution conducts electricity and has a pH of 6. The possible identities of this are A, carbon dioxide, B, water, C, sodium chloride, D, cobalt-2 nitrate. D, cobalt always produces red, pink, okay, salts, okay, that would obviously conduct electricity because it's an ionic compound, okay, things like that. So that's something I might ask you to do. That's just using the information that's in lesson 4. Okay. All right, then we talked about solubility. That's lesson 7. Lesson 7 is another read and regurgitate kind of a lesson. Okay? So go over it, know the terminology, homogeneous, heterogeneous, okay? Solution, solute, solvent, precipitate, okay? Those terms. Know how to use your solubility chart. We talked about that already. Okay, that will certainly be part of that lesson as well. So this stuff would be mostly in the multiple choice, at least for the terminology part. Same with using the solubility chart, that would probably be multiple choice as well. If you've done the practice test, the last question in the practice test is kind of an application question of solubility. And I always ask a question like that on every test and every unit, a question about, okay, I taught you this stuff, but I never talked about this particular situation. I want to see if you can transfer what you've learned to that situation and apply it there, okay? So I think that question involves trying to take something out of a solution or something like that, and so you'd have to use terms like precipitate and maybe a double replacement reaction, solubility, okay, things like that. Okay, that sort of makes sense? In that lesson as well is all the stuff about water being a polar molecule. Okay, so the polar nature of water. So you also need to know what it means to be a polar molecule. Okay, so in a polar molecule, the electrons are shared, but they're not shared equally. Okay? One of the two materials in that compound is more electronegative. That means it pulls the electrons toward it more. So if we're talking about water, okay, water is a polar molecule because oxygen holds onto electrons more tightly than hydrogen does. So the electrons end up down at the bottom of the molecule with oxygen, and the two little hydrogen nuclei are at the top with no electrons. Okay? And what happens there is this. Okay? This ends up being positive. This ends up being positive because the electrons are hanging out down here. Okay? So even though it's not overall a charged particle, it acts like it is because the electrons end up being at the bottom. Now, if another water molecule starts to move towards this one, its negative end and the positive end of the one I've drawn already are going to what? Yeah, they're going to attach to each other. They'll be attracted to each other because opposites attract, okay? And because this end is negative, they will form a bond. What kind of bond? A hydrogen bond. Okay, hydrogen's involved, so it's a hydrogen bond. Okay, hydrogen bonds are weak. They break, but they reform very easily. Okay, polar molecules that have hydrogen bonds will show two behaviors. You remember what they are? Cohesion and adhesion. Okay, cohesion is what I drew here. Water to water. So the same molecule to the same molecule. Okay? Adhesion is that molecule to something else. Right? So here would be your two examples. Surface tension is cohesion because it's water to water. Okay? So that's why you get a drop of water has that kind of shape to it, like a bubble. A water droplet stuck to the side of a glass is showing you adhesion. The water is adhering to the glass, and it's not sliding down. Right? Everybody kind of follow what I mean there? Okay, so hydrogen bonds between like molecules, cohesion. Hydrogen bonding between unlike molecules, adhesion. The example we talked about in class was the plant. Okay? The plant used the polar nature of water to bring water up the plant, okay? Like a barrel of monkeys, right? The hydrogen bonds, cohesion linked the water molecules together, but they could also stick to the inside of the stem using adhesion, and that kept them from falling back down. Okay? Go over that lesson, make sure you know those points. I will certainly have probably a numerical response question that asks about those concepts. All right, any questions on that? Okay, so like we said, what's a polar molecule? We just talked about that. Okay, cohesion and adhesion, we just talked about that. Okay. And then real world examples, so we talked about the plant, we talked about the Jesus lizard, okay, those kind of things. Yep. Okay, next thing we went over, most important thing in the whole unit, reactions. Okay, reactions are worth somewhere between 1/4 and 1/3 of the marks on your unit exam, either directly or indirectly. So they are the most important thing to know well. Okay, we went over 5 types. What are they?
Combustion,
Combustion reaction, synthesis reaction,
Double replacement.
double replacement,
Single replacement.
single replacement, decomposition. Those are our 5 types. Okay, there will definitely be multiple choice items where it'll be, here's a reaction. It is an A, decomposition, B, combustion. Okay, be able to identify the types. You also have to identify the types if you are predicting the products, something you will be asked to do in the written response part of the test. Big marks there. Okay? Every reaction is worth 4 marks, so okay, pretty big. So be able to identify the types, okay? Obviously be able to predict products and balance. Okay, write your reactions out and balance the reactions. Okay, so you've got a couple of quizzes with reactions questions on them that you can refer to. You got your assignment back before we left. Okay, and you got lots of worksheets on reactions as well. There's reactions in the exam prep package as well. Okay, so lots of things you can use there. But for now, predict the products of these reactions and balance them. So 1, 3, and 4, I already wrote the reactants out for you. All you have to do is write out what I have there and predict the products and balance. 2 and 4, I wrote in words. So you need to write the reactants and then predict the products. All formula form, all balanced. Okay, give you a few minutes to try those ones. Oh, I left one of the balancing numbers in there. Okay, so reaction number 1, I only have 1 reactant. Okay? What kind of reaction starts with only 1 reactant? Decomposition. Okay, in a decomposition reaction, okay, the atoms will separate according to Dalton. All right, so that means I'll have nitrogen, which is a special element, and oxygen, also a special element. How important is it for me to remember that? Very. I won't get it right if I don't. Okay, so now I've got those 2. Now that I've got the products, now I need to balance this. Since it's not a combustion reaction, I start with the biggest number. That would be 3. All right, I've got 3 nitrogens in the reactants, only 2 in the products. Lowest common multiple is 6. Okay, so this side I will multiply by 2, and this side I will multiply by 3. Now I have 6 nitrogens on each side. Right? This 2 also applies to the oxygen, giving me 4 oxygens in the reactants. But I only have 2 here in the products, so I will also need a 2 in front of that. Now the reaction is balanced. Okay, ringing a bell. Decomposition reactions are one you always have to be wary of because you're probably going to produce a special element or 2. Okay, in those cases. So it's always something you have to be on the lookout for. Okay, is that a special element with the right number on it? Okay, all right, question number 2. This one's written out in words. So I've got copper 2 sulfate. So Cu with the 2+ charge with sulfate, that's a -2 charge. That already adds up to 0, so this compound is fine the way I wrote it. And it is reacting with lithium nitride. So Li, that's a +1. Nitrogen's a -3. Drop and swap. Okay. What kind of reaction is that? That is a double replacement reaction. 2 ionic compounds are reacting. in a double replacement reaction, what's the pattern tell me to do? Switch the metals. Switch the metals, right? That way I'll get two new ionic compounds. All right, so all I'm going to do is swap lithium and copper. So lithium will wind up with sulfate. Copper will wind up with nitrogen. Okay, I just made two new ionic compounds. What did I not do to either of them? I did not drop and swap either one, so it's important that I do that now. This is a +1, and this is a -2. So when we drop and swap, we'll have Li2SO4. Okay. On this side, copper was a 2, so it's also a 2 over here. Nitrogen's a -3. Drop and swap. Okay. Now I need to what? I have to balance. Right? I've got everything written correctly, but the reaction isn't balanced yet. Okay? The biggest number is 3. It's on both copper and lithium. Copper has the bigger charge, so we'll balance it first. There's 3 over there. Now there are 3 in the reactants. That 3 also applies to the sulfate. So I've got to go here and put a 3 there. Now I have 3 sulfates on both sides, but that gives me 6 lithium. 2 times 3 is 6, so now I have 6 lithiums on both sides, and that 2 applies to my nitrogen, so there's 2 nitrogens here and 2 nitrogens over there. We're good. Now it's balanced. Okay, about as tricky as balancing would get for a double replacement reaction. All right, questions on number 2? What kind of reaction is number 3? What are always the products of a combustion reaction?
Water and CO2.
Right, CO2 and water. Okay, so carbon dioxide and water. Okay, are there special rules for balancing these type of reactions? Yes. I balance in what order? Yeah, CHO, alphabetical order. Okay, and what's the other rule? Right, the rule of 2. If there's an even number of, which atom? Of carbon, right. If I have an even number of carbon, which I do, okay, then I start with a 2. Do I do that if I have an odd number? No. Okay, only evens. Okay, you can remember it this way. 2 is the first even number. It goes with any even number of carbons. Okay, all right, now I can balance alphabetically. I have 2 times 4 is 8 carbons. Now I have 8 carbons on both sides. I have 2 times 10 is 20 hydrogens. Now I have 20 hydrogens over there. Now I can balance my oxygens. There are 10 oxygens in the water. There are 8 times 2, okay, is 16 here. 16 plus 10 is 26. 13 times 2 is 26. Now it's balanced. Okay? I would expect to have a couple of those on your unit exam. Probably one that's just a balancing question and probably one that's like this. Okay? So that means you probably have one where you need the rule of 2 and one where you don't. Okay? That would be me assessing whether you remember when to use it or not. Okay, what kind of reaction is number 4? It's a single replacement reaction. So we've got tin, the 4+ kind, with oxygen, which is a -2. All right, so when I drop and swap, I get 2 and 4. I got to reduce, right? 2 and 4 can be reduced down to 1 and 2. Okay, so tin 4 oxide looks like that, and it's reacting with nitrogen gas. What do I have to remember about that? It's N2, right? It's special. Okay? This is what makes single replacement reactions the trickiest. There's so much to remember. You're often going to get special elements in either the reactants or the products or both, and you're always going to get an ionic compound that you have to drop and swap. Okay? So, in a single replacement reaction, the pattern says whatever the lone element is, that gets swapped out of the ionic compound. Nitrogen's a nonmetal, so it's going to swap out the oxygen. So tin will wind up with nitrogen. Oxygen will wind up alone. Okay, do I have any special elements in the products? Okay, which one? Oxygen comes as a? Right. Okay, and I have an ionic compound that needs to be dropped and swapped. I was told tin was a +4, okay, and nitrogen is a -3, drop and swap, SN3N4. Okay, now I can balance. Biggest number is 4. Okay, there's 4 nitrogens on this side. Now there are 4 nitrogens on this side. There are 3 tin here. Now there are 3 tin in the reactants. That gives me 6 oxygens. 3 there will balance my oxygens. Okay. Questions on that one? Okay. Last one. What kind of reaction is that? It's a synthesis reaction. What did I do in this one? I flipped it, right. What element do I need to write first in my products? The lithium, because I'm going to make an ionic compound. This is a nonmetal, and this is a metal. So I have to remember that when they go together, they make an ionic compound where the metal is listed first. Okay, then I drop and swap. Okay, so Li3P, and then balance. 4 is the biggest number. That should do it. Okay. I'm not going to ask ones any harder than that on your unit exam. Okay. All right, questions there? What was the last thing we went over? Mole equation. Okay, now there was something I skipped over, okay, which I'll go back to here. Okay, yes, the mole equation is the thing that we haven't done yet, but I also skipped over that we did talk about the scientific method. Okay, that's what you use when you're doing a lab report and you're deciding what your manipulated variable is and what your responding variable and stuff like that. So expect you could get a multiple choice question about that. It could go something like this. A company is wanting to test bulletproof glass for use in a bank. Okay? In their experiment, they have 4 different sheets of glass, each one of a different thickness. Sheet 1 is 1 centimeter thick. Sheet 2 is 2 centimeters thick. Sheet 3 is 3 centimeters thick. Sheet 4 is 4 centimeters thick. Okay? Each one of these sheets of bulletproof glass will have the same weapon fired at it from the same distance in the same room. Okay? The experimenter will be measuring or observing how deep into the glass the bullet penetrates or whether the glass shatters or not. What's the responding variable in this experiment?
Whether the glass shatters or not.
Right, the observations made about the glass, depth of penetration or shattering of the glass. Okay, that's scientific method. So expect that I'd give you an experiment, you would have to determine what the variables in that experiment were. Okay? In that experiment, what were some controlled variables? The weapon, okay? The distance it was shot at, temperature of the room. Glass is more brittle at lower temperatures, okay? So making sure that they were all in the same room means they were all the same temperature. Okay, making some sense? So I'd certainly ask that. Okay, there are 4 types of mole equation questions. Right before we were so rudely interrupted, we had spent a few days talking about the different ones, and I had gone over a few examples of each one. In fact, we did several examples of each one each day for almost a week. And so you have a whole bunch of examples of each type. There are 4. Okay, so what I'm going to do is put up a couple here, and let's see what we remember from this. Okay, I'll give you a few minutes to work on those. You got one of each type there, but they're not in order. All right, so in our first one here, we're looking for mass. Mass is little m. Okay, we're told n, the number of moles, 16.2 moles. Okay, and we're told the material is calcium chloride, so that's CaCl2. Right, calculating the molar mass of that, calcium is 40.08 plus 35.45, that's the chlorine, times 2 should give us 110.98 grams per mole if my mental math is right. Is my mental math right? Okay. So I've got these two numbers, n and big M. Mole equation is n equals little m over big M, but I'm trying to solve for little m, so I need to multiply both sides by big M to isolate the mass. Right, now that I've done that, now it's big M, 110.98 grams per mole, times 16.2 moles. Okay, the moles will cancel, and I'll be left with grams. Okay, so 110.98 times 16.2, all right, 1,797.88 grams. All right, that's a type 2 question. Any questions on that one? Okay, how many people have done number 2? Okay, let's have a look at number 2. So in number 2, we're looking for the number of molecules. So will I need Avogadro's number for this one? Okay, remember that Avogadro's number is 6.02 times 10 to the 23, and it is the number of particles in a mole. Okay. Now, it tells us that the material here is beryllium bromide, BeBr2. So that'll be 9.01 plus 79.9 times 2. It's like 168 or something. So 9.01 plus 79.9 times 2, 168.8. Okay, grams per mole. All right, so I've got that, and they told me the mass, 165 grams. Okay, I have big M and little m. What can I calculate right now? Little n, the number of moles. Okay, so I should do that first. N equals little m over big M, so 165 grams divided by 168.81 grams per mole. The grams will cancel. This is about 0.97 moles or something like that. Okay, so 165 divided by that number. Okay, 0.977. I'm just going to write 0.97. I'll use all the decimals that are in my calculator. Okay, now that I have the number of moles, I want to know the number of molecules. Am I multiplying or dividing by Avogadro's number here? Multiplying. I need a big number. The number of molecules is going to be an absolutely incredibly large number. Okay, so number of molecules, okay, is n times 6.02 times 10 to the 23. So in this case, that would be 0.97 times 6.02 times 10 to the 23. So in my calculator, that'll look like this. All right, I'm going to take that number with all the decimals, and I'm going to multiply it by, in brackets, 6.02, second comma button to get the E, 23, close the brackets. All right, so 5.88 times 10 to the 23 molecules. Okay, ringing a bell? How important are units? Well, if you want to get full marks, they're important. Because if you wrote 5.88 times 10 to the 23 and didn't write molecules after it, it's wrong. Okay, an answer without units is wrong. Because I don't know whether it's apples, oranges, people on pachyderms, I don't know, okay? It's got to have units on it, okay? All right, how many people are done 3? All right, I'll give you a few more minutes on 3 and 4, and then we'll go over those before class ends here.
Okay, let's look at 3 and 4 here real quick, guys. So how many moles of lithium oxide are in 78 grams? Okay, so we're looking for N, and that's the number of moles. Okay, big M, lithium oxide, that's going to be Li2O, so that'll be 6.94 times 2, oh, not times 10, times 2, okay, plus 16. 6.94 times 2 plus 16. Okay, so we're looking at 29.88 grams per mole. And we're also told the mass, 78 grams. Okay, so we're looking for N, which just means I'm plugging in the numbers here. This is a type 1 question. 78 grams divided by 29.88 grams per mole. Grams are going to cancel, and I'll be left with moles, and it's just 78 divided by 29.88. Okay, so for that one we got 2.61 moles. Okay, questions on that one? Okay, so number 4, okay, is probably the most involved. It's a type 4 question. We're told the number of moles, or sorry, the number of molecules, and we are looking for the mass. Okay, so we got number of molecules, okay, and that is 7.49 times 10 to the 24. We're looking for mass, okay, and we know the material is water, so H2O. So that'll be 1.01 times 2 plus 16, 18.02 grams per mole. Okay, if I want to get little m, I need n. I need the number of moles. I don't have it right now. Okay, how do I get it? Divide by Avogadro's number, right? N is the number of molecules, 7.49 times 10 to the 24, divided by the number of molecules in 1 mole, 6.02 times 10 to the 23. So this probably be a bigger number. Okay, so 7.49 E24 divided by 6.02 E23. All right, so I have 12.44 moles. Okay, now that I have N and big M, now I can get little m. N equals little m over big M. Multiply both sides by big M, and we've got our 18.02 grams per mole times 12.44 grams, moles. Okay, so the moles will cancel, and I'll be left with grams. All right, so we're looking at 224.20. Okay, that's what will be on your exam on Monday. Okay, we've gone over everything in this unit, so you're ready. Just spend the next couple of days looking over things. Do the review if you haven't already. Do it again if you did. Okay, come and see me if you have questions. Okay, that's what I'm here for, so make sure you pop in and ask questions.